Today I'm going to go through complex numbers in polar. So the first proof that I'm going to run through is e to the power of I theta is equal to cosine theta plus I sine theta, also known as Euler's formula. So this really smart guy called Euler came up with this formula, but a really common problem in students is that they use this formula, they plug it in without really understanding how it's derived, and this really causes them to hit a wall when it comes to examinations because there's really a lack of understanding and it peats them in that way. So Euler's formula, how to derive it is basically using the Maclaurin expansion series, e to the power of x is equal to 1 plus x squared over 2 factorial plus x to the 3 over 3 factorial, and so on and so forth, with each term following the form of x to the n over n factorial until infinity. So we have, all we need to do is to let x be equal to I theta, and we get e to the power of I theta is equal to 1 plus I theta minus theta squared over 2 factorial plus, minus theta to the 3 over 3 factorial, imaginary, plus beta to the 4 over 4 factorial, it's real, plus I times theta 5 over 5 factorial, and so on and so forth. And now what I'm going to do is I'm going to group them up in terms of real and imaginary. So we have 1 minus theta squared over 2 factorial plus theta to the 4 over 4 factorial, and so on and so forth. And on the other side we have I times theta minus theta to the 3 over 3 factorial plus theta to the 5 over 5 factorial. And if you realize, what this looks like is two more Maclaurin series expansion, which is cosine theta, and on the right side we have sine theta. So we've effectively proved that Euler's formula actually can be derived quite simply using Maclaurin series expansion. Right? So we've distilled down one Maclaurin expansion to two series of expansion. And the conjugate of the Euler's formula, so the conjugate of e to the power of I theta is equal to e to the power of negative I theta. And why so? Is e to the power of negative I theta, right? E to the power of negative I theta is the same thing as this, and that's equal to cosine of negative theta plus I sine negative theta. And because cosine theta is equal to cosine negative theta, we have cosine theta, and because sine of negative theta is equal to negative sine theta, we get it expressed in this way, right? And this is the conjugate of e to the power of I theta. Now I'm going to prove x plus iy is equal to r times cosine theta plus I sine theta. And take note, this is still in Cartesian mode because it's still in a form of a plus ib, but then using the Euler's formula we get r e I theta. So this is the polar form. So now let's have an Argand diagram over here. Argand diagram is basically plotting the imaginary against the real axis. And this is called the Cartesian mode because let's say we have a point xy, right? In the Cartesian mode, what this point denotes is that it's moving x units in the real direction and y units in the imaginary direction. But in the polar mode, every single point is denoted by the distance of the point from the origin, r, and the specific theta value it's making with the real axis. So in this way, right, when we talk about the polar system, we can actually denote every single point inside this 2D space. So let's say we have one point over here, P, and one point Q over here, right? This P has a specific R value and a specific theta value, R1, theta 1. And this point over here can be denoted by a specific R value and theta value. So I'm no longer using the Cartesian coordinates. It's now being denoted by R values, the diagonal distance from the origin, and the accompanying theta value. So now I'm going to isolate this right angle triangle out here to show you how we can prove the above formula. So this is the real axis, the origin, r, x, y, and the theta, the angle theta, and this is the point xy. Right? Using basic trigonometry, we get x is equal to r cosine theta, and y is equal to r sine theta, right? Because r is the hypotenuse. So with this, we can get x plus iy is equal to r times cosine theta plus I sine theta. But this is not just what we want. We also want to change it to polar form, which is r e-i-theta. So this is what we need to find out. And how do we find theta and r? R is equal to the square root of x squared plus y squared, right? Because this is the diagonal distance of the point from the origin, right? R is the hypotenuse. And using Pythagoras theorem, we can get that. So R is, in fact, we call it the modulus of the complex number. The modulus of the complex number is equal to square root of x squared plus y squared. Right? And theta is equal to, or theta in this case is equal to tangent inverse of y over x, right? Because tangent theta is equal to y over x. Right? And this can be called the argument of the complex number. Alright, so these are just two terms that are introduced to denote r and theta value. And how we can get r e-i-theta is, well, let's have an example. Let's say x plus iy is equal to 1 plus I root 3. Well, and that's equal to, so in fact, r value is equal to its modulus, right? So it's the square root of 1 squared plus root 3 squared. That's 1 plus 3. And ei tangent inverse of y over x. So tangent inverse of root 3 over 1. And you get pi over 3. So it's ei pi over 3. And you get 2ei pi over 3. Right? And just to check whether it works, we have 2ei pi over 3 be equal to r times cosine theta plus I sine theta. So it's equal to 2 times cosine pi over 3 plus I sine pi over 3. We get 2 times half plus root 3 over 2. Sorry, I root 3 over 2. And we get 1 plus I times root 3. Right? Which is correct. The properties are the intermediate step linking the proofs which we have already derived to the applications. So let's work with these two complex numbers, z be equal to r e-i-theta and w be equal to q e-i phi, which is basically another set of r e-i-theta, but we need to express in a different way. So we have the product of these two complex numbers, zw be equal to rq e to the power of I times theta plus phi, and the result of z over w be equal to r e-i-theta over q e-i phi, and that's equal to r over q. R over q is its modulus, and we have e times theta minus phi is equal to its argument. Right? The number over here is always a complex number's modulus, and the number over here is always its argument. So the first proof is about the product of complex numbers. So the first proof would be the modulus of zw be equal to the modulus of z times the modulus of w. Now this is really self-explanatory because the modulus of zw is equal to the distance of this complex number from the origin, and that's rq, right? So the left hand side is equal to rq, right? And the right hand side is equal to the product of individual modulus. So on z it's r, and on w it's q. Right? So the modulus of z is r, and the modulus of w is q. And when you equal them, right, I mean the product is the same, so it's equal. So the right hand side is equal to left hand side. Right? The argument of zw, right, you realize it's equal to the argument of z plus the argument of w. Alright, and how to prove it? The left hand side of zw, it's theta plus phi. Right? So the left hand side, it's theta plus phi, and on the right hand side, the argument of z, it's equal to theta. Alright, and the argument of w is equal to phi. And so this is equal to the left hand side. Again, alright, and the second set of properties is about division. Alright, so the modulus of z over w is equal to the modulus of z over modulus of w. So the importance of proving these properties is that later on, when you want to use these properties, when you want to segregate the numerator and denominator, it really makes life easy by really claiming that, yeah, you have the rights to segregate them because you've already proven that, right, it's possible to do that. So the left hand side, the complex number over here is this one over here, and the modulus is r over q. R over q, and the right hand side is equal to the modulus of z, r, over modulus of w, which is q, and that's equal to the left hand side. Right, and the argument of z over w is equal to the argument of z minus the argument of w. Right, and the left hand side, as shown over here, is this number. It's theta minus phi, and the right hand side is equal to argument of z, which is theta, minus argument of w, which is phi, and that's equal to the left hand side. Right, so we have now a few generalizations. The product and division can be segregated. So the product of complex numbers or the division, right, can be segregated when it comes to modulus. And the argument behaves like, what does it behave like actually? It behaves like a ln function, right? Because when you have ln of AB, right, ln of AB is equal to ln of A plus ln of B, right? And when you have ln of A over B, it's equal to ln of A minus ln of B. So in fact, the argument behaves like a ln, right? So it behaves like a ln, but I'm not saying it's like a ln, but I'm not saying it's a ln, but argument behaves like a ln. And this can also derive one more factor, which is one more property, which is that, right, same thing as ln, the power function exists. So in fact, ln of a to the power of 5 is equal to 5 ln a, right? Or similarly, in the argument of let's say E-i-5-theta, right, is the same as having the argument of E-i-theta times E-i-theta, right, all the way onwards 5 times. And that's the same as having argument of E-i-theta plus argument of E-i-theta 5 times. And it's equal to 5 argument of E-i-theta, right? So argument behaves like a ln. So now let's move on to some applications. Given the modulus of 2iz, this complex number is equal to 6, and the argument of 2iz is equal to pi over 4, express z in Cartesian form. So, well, 2iz is, you want to get rid of the 2i because you want to express z, right, in Cartesian form. So, first thing, the modulus of 2iz is equal to the modulus of 2i times the modulus of z, right, according to our previous property. And this gives us, or the modulus of 2i is just 2, right? Or in fact, you can even split them further to the modulus of 2, the modulus of I, and the modulus of z. And that's equal to 2 times 1 times modulus of z. That's 2 modulus z. And it's equal to 6, right? So we get the modulus of z is equal to 6 over 2, that's 3. Right, now let's talk about argument. The argument of 2iz is equal to the argument of 2i plus the argument of z. Right, the behaves like a ln, and that's equal to, what's 2i's argument? Well, I on an Argand diagram, right, I is over here. So the argument is equal to 90 degrees, which is pi over 2. And we have pi over 2 plus argument of z, and that's equal to pi over 4. Alright, so the argument of z is equal to pi over 4 minus pi over 2, and that's negative pi over 4. Right, so negative would be in this direction, negative pi over 4. So we have z is somewhere over here. Right? See, the modulus is 3 and the argument is negative pi over 4. Right, so we have z is equal to, now I want to use this Cartesian form, right? So we have the argument and the modulus, so i.e. we have the r value and the theta value, so we need this formula, right? Because we want to express it in terms of x plus iy. So we have z is equal to r times, so r is 3, and theta is equal to negative pi over 4. So that's, or you just sub it in actually, because you've already proven and you already know why the proof exists, so you can just substitute it in to aid our application of it. So that's z is equal to 3 times cosine negative pi over 4 is equal to cosine pi over 4, and that's equal to root 2 over 2. Right? Negative of a theta value, or negative goes out, so that's minus I sine of pi over 4, that's equal to root 2 over 2 as well. And we get 3 root 2 over 2 whole thing times 1 minus I. Right, so we have finally expressed z in terms of Cartesian form, which is in terms of x plus iy. Well, the next one looks a little more challenging simply because there's more variables on one side and on the other side, but really once you break it down into what you need to do, you can solve it easily. So in fact, these are in Cartesian coordinates, but which one is better to work with when it comes to powers? In fact, polar form makes it really easy to work with powers, right? So now we need to change it into the form of E-i-theta, and these two, in fact, they are conjugates of each other if you realize. Right? These two will be so much easier to work with. So let's try to change from a -1 plus I root 3 to polar form. So this is changing from x plus iy into E-i-theta. So what is the value of r? Right, the value of r is equal to the square root of x squared plus y squared. So it's -1 squared, that's 1, and root 3 squared, that's 3. Alright, E-i-theta. So you don't know what theta is yet. Let's draw an Argand diagram over here. So we have imaginary against real. Right, -1 plus root 3 I, and that's -1 root 3 I. It's over here. This height is root 3, and this is 1 in length. This gives you -1 plus root 3. And what is this theta value over here? Right? I mean, you know that the tangent inverse of root 3 over 1 is equal to pi over 3, right? So in fact, this value is simply equal to pi minus pi over 3. And that's equal to 2 pi over 3. That's equal to 2ei 2 pi over 3. In fact, this is the E-i-theta form, and that's so much easier to work with when you times to the power of n, right? So what, -1 minus I root 3. So in fact, if you recall in the first proof, right, the conjugate of E-i-theta is equal to E negative I-theta. Right, so without working, you can already quote that -1 minus I root 3 is equal to 2ei 2 pi over 3 conjugate. Right, it's equal to its conjugate, and that's equal to the E negative I theta. So it's E negative I theta. Alright, and from here you can see that it's so much easier to work with because the left hand side is equal to 2ei 2 pi over 3 to the power of n plus 2ei negative I 2 pi over 3 to the power of n, and that's equal to 2 to the power of n ei 2n pi over 3 plus 2 to the power of n e negative I 2n pi over 3. Right, and this can be factored out to simply be an addition of this complex number and its own conjugate. A really interesting fact is, if you have E-i-theta plus its own conjugate, right, what do you actually get? You get cosine theta plus I sine theta plus cosine theta minus I sine theta. In fact, this gets rid of all the complex components, and this gives you 2 cosine theta, a real number. Right? And this looks something like that already, right? So when you have 2 to the power of n times that over there, right, we get 2 to the power of n times cosine, this is theta, right? So we have cosine of 2n pi over 3. Right, let me show you that it's really not that hard when you break it down to polar form. Right, cosine 2n pi over 3 plus I sine plus this over here. Right, cosine of negative theta is equal to cosine theta 2n pi over 3, and sine of negative theta is equal to negative sine theta. Right, this looks exactly like the form over here, and that's equal to 2 to the power of n times, right, this will cancel out with each other. You get 2 cosine 2n pi over 3, and it's looking more and more like 2 to the power of n plus 1 cosine of 2n pi over 3, which is equal to the right hand side. So effectively in this episode, we have been through the proofs, the properties, and finally the applications of complex numbers in polar. And you can see that, right, you can in fact make amazing proofs like these, right, really simple, just by converting them into e-i-theta and using e-i-theta to convert back into cosine theta plus I sine theta like we did over here, right? From this step to this step, it was converting from polar coordinates back into Cartesian coordinates.